In the world of chemistry, there's this silent duel that's fought every single day. A molecule faces a choice. Does it go for a swift, direct attack? Or does it play the long game with a patient, two-step strategy? This is the story of substitution, and today we are stepping right into the ring. Let's get into it.
So, picture this. You've got a haloalkane molecule. It's our main character. And closing in on it is an attacker rich with electrons, a nucleophile. Does our molecule strike back right away? Or does it wait for the perfect moment? Now this choice, it's not random. It's a calculated move, and it's governed by the unwritten laws of chemical combat.
All right, let's meet our fighters. In this corner, we have the SN1 reaction, and in the other corner, the SN2 reaction. Their goal? Totally the same, substitution. But their methods? They couldn't be more different.
Let's look at the tail of the tape here. SN1 is our patient strategist. It's a two-step process. It forms a nice, stable intermediate. It takes its time. But SN2? That's the direct attacker. It gets the job done in one single, swift move. And this tiny difference in timing, believe me, it changes everything, from how fast the reaction happens to the final 3D shape of the molecule you end up with.
So how does this direct attacker actually work? Well, the SN2 playbook really only has one move, but it's a good one, the backside attack. The nucleophile literally ambushes the carbon from the side opposite the group that's trying to leave, kicking it out in one single fluid motion. And the result? It's incredible. The molecule's whole geometry flips inside out, kind of like an umbrella getting caught in a gust of wind. It's a beautiful process called a Walden inversion.
The patient strategist, SN1, plays a completely different game. First, the leaving group just up and leaves. This breakup creates a flat, positively charged intermediate that we call a carbocation. And this is the moment of vulnerability. Because it's flat, the nucleophile can now ambush from the top or from the bottom. This leads to a 50-50 mix of products, what chemists call a racemic mixture.
Okay, so we've got two very different strategies. But how on earth does the molecule actually choose which path to take? Well, it all comes down to the rules of engagement, the specific conditions of the duel.
And the number one rule of this duel is this: structure is everything. Just look at the table. Tertiary carbons, those are the ones crowded with three other carbons. They're like little fortresses. They are way too bulky for a direct SN2 assault, which forces the patient SN1 approach. But primary carbons? Oh, they're wide open, basically sending out an invitation for that swift SN2 backside attack.
But what about secondary carbons? They're the battleground state, right smack in the middle. They could really go either way. And for these, the winner is decided by two other critical factors: the battlefield itself, that's the solvent, and the strength of the attacker, the nucleophile.
Let's talk about the battlefield, the solvent. Polar protic solvents, think water or an alcohol, they have these available hydrogens. They can form a kind of protective cage around that carbocation's intermediate, basically acting as the hype crew for the SN1 pathway. But polar aprotic solvents like acetone, they don't have those hydrogens. They just leave the attacker alone, completely unhindered, clearing the path for an SN2 victory.
And finally, we have the attacker itself. A strong, aggressive nucleophile, it is not going to wait around. It's going to force a direct SN2 reaction. It just wants to get the job done. But a weaker, more patient nucleophile, like water again, is perfectly happy to just wait for that leaving group to depart on its own, allowing the SN1 reaction to just happen.
But just when you think you've figured it out, that this duel is just between two contenders, chemistry throws a curveball. What if the molecule decides to reject substitution altogether and chooses a third path?
This all comes down to a question of steric hindrance. What happens if our attacker is a really strong base, but it's just too bulky to perform that precise backside attack it needs for an SN2 reaction? It literally can't get in to substitute. So, what does it do?
It switches tactics entirely. Instead of trying to attack that crowded carbon, a big, bulky base like tert butoxide just plucks off a much more accessible hydrogen from a nearby carbon. This triggers a little chain reaction, which eliminates the leaving group and poof, forms a double bond. This is the E2 reaction. It's a powerful competitor that changes the game from substitution to elimination.
So now we have this intense three-way competition: SN1, SN2, and E2. But some molecules are what you might call conscientious objectors. There's a whole class of them, the haloarenes, that simply refuse to play this game at all. Let's find out why. Haloarenes are incredibly stubborn, and there are 4 key reasons why.
First off, the bond connecting the halogen to that aromatic ring has partial double bond character. It's just extra strong. Second, the ring itself is super stable because of resonance. It hates to be changed. Third, the ring physically blocks any attempt at a backside attack. No way. And finally, even if the leaving group did leave, the carbocation it would form is wildly unstable. So for both SN1 and SN2, it's pretty much game over.
But you know how it is with all the good rules in chemistry. There is always a very specific, very important exception. Under some pretty extreme circumstances, you can actually force a haloarene to undergo substitution. But it's going to need some help.
And that help comes in the form of a nitro group. This thing is a powerful electron withdrawing group. If you stick one of these at just the right spot on the ring, the ortho or para position, it pulls electron density away, which stabilizes the intermediate and allows a special kind of substitution to happen. It's like the one cheat code to make these unreactive haloarenes finally play the game.
Whew! Okay, we've covered strategies, battlefields, game-changing twists, the whole shebang. Now, let's condense all of that into the ultimate playbook, your personal guide to predicting the winner of any chemical duel. Here it is, your final playbook. Tertiary carbon, it's going to be SN1. Primary, SN2 all day. Secondary, that's when you've got to check your solvent and your nucleophile. See a big, bulky base? Immediately think E2 elimination. Got an arrow halide? It's probably a no-go, unless you see that nitro group cheat code. And of course, remember that better leaving groups make for faster reactions, and the final 3D shape, whether it's that racemic mix or a full inversion, tells you exactly which path was taken. You see, at the end of the day, understanding these reactions isn't really about memorizing a bunch of rules. It's about being able to read the battlefield, knowing the contenders, and then predicting the outcome of the duel. Chemistry is a story of conflict and resolution. It's just written at the molecular level. So now that you know the rules of engagement, what story are you going to predict next?